Okay, in this video, I'm going to go over some of the quirks of BASIC and the ROM, how they relate to assembly language programs in this editor here. Bling. Okay, so here we go. We're going to load up the editor. Okay, very first thing I'm going to do is we're going to go to the end of RAM, just below the memory mapped I/O. And you can see that there is some data here. Now this should all be blank. So if we hit F5, you can see that the data stored at the very end of RAM is the file name that I entered when I was in immediate mode in BASIC, when I typed in load edit.prg. So when you are using BASIC and assembly language together, this is something to keep in mind. BASIC needs to be told what areas of RAM are off limits. It needs to be told where the memory top is, or it will use that memory that it thinks is free and available for things like file names and such, and variables. It will start storing strings. So if you have an assembly language program that is at the end of RAM, and then you start using BASIC as well, as if BASIC doesn't know that that RAM is off limits, it will start overwriting your assembly language program. That is something to keep in mind. You have to tell BASIC. So the second thing I want to do is we're going to go to the JSR far function in the kernel. Now this here is a jump table, the kernel jump table. It's where all of these functions are located in, well, they point to where the functions are actually located in RAM. And you can see that they're not all every 3 bytes. There's a couple extra bytes thrown in here. So if I scroll up, you can see where some of the other labels are located. But JSR far is the one we're interested in, and it's at E2A9. So I'm going to go to E2A9, and I'm going to set a label here. So this is where the actual JSR far function is located. So we can read through it, and you can see that first thing it does is it stores all of the important variables, all of the registers. And then it starts looking through the stack, and it finds the return location and adds 3 to that and stores it back in the stack. And then it starts loading. The next 2 bytes that it loads are a word, which correspond to an address somewhere in banked RAM or ROM. And it checks that high byte to see if it's greater than C0. And if it is, it goes into the ROM version, where it loads the 3rd byte as the bank, ends it with number 7. In future versions of the emulator, if they go to 32 banks, this will be ended with 1F. And then it does the function, it does the actual far call, changes the ROM bank pointer, and jumps to a routine in low RAM at 02C4, which then takes care of actually calling the routine 02E1 down here. You can see this call is the actual subroutine call in the other bank. And you can see that's actually down here. It's this jump, and so when your subroutine returns, it returns to 02CC, which then loads up all of the data that's needed and stores the processor status register. It loads up the old ROM bank number, stores that in the ROM bank, and then it loads up the processor status register, which is right there, and copies it to this point here. But if we go back, if we go back, if it's less than C0, if it's a RAM bank call, it branches to E2, E5. Go down here to E2, E5, and I'll just hit F1 to bring it to the top of the screen. E2, E5 does exactly the same thing. It doesn't end it with, and the bank number with 7 like the ROM bank call does. But then it does the same sort of thing that we saw down in low RAM at and calls 02E1. Okay, that same call that we just had a little earlier with the RAM bank. And then it does the same thing, loads up the old RAM bank pointer, but it's missing something here. It does not copy this value into here. This value here is still the old RAM bank pointer. So when you're using JSR FAR with RAM banks, the value that's stored in your processor status register is actually the old RAM bank value. Now I've raised this issue on GitHub, but it's going to take until the next time they actually update the ROM on the emulator for that to be fixed. So if I execute null is just a program that's only command is return. So the processor status register, that's that NV octothorpe BDIZC over there. It's all the flags. It's the collection of all your flags. So that's replaced with the bank number instead, the return bank number. So to get around that, I copied JSR FAR down here, and instead, if it does exactly the same right up to this point, but if it's ROM bank, it just breaks off to the JSR FAR routine, which handles it all correctly. I've replaced the RAM bank pointer. I've actually put this into 0 page at 4243, so that's hence all of this load A 0 page indirect 42 story 0 page indirect 42. That's the RAM bank pointer. So it does exactly the same thing, but at this point, then it goes to 02D6, which is that part in ROM that is exactly the part that the ROM version of the JSR FAR routine ends up with, which correctly stores the pointers, the flags in that processor status register position in the stack. So JFAR is JSR FAR, but it works correctly for both ROM and RAM banks. And the change that they need to make to the ROM is just a simple jump that they can put in, and I've shown them where to put it, but like I say, it's going to have to wait until they update the ROM. So until that ROM gets updated, you can use JFAR. When they update that ROM, the first 3 bytes of JFAR will just be a jump to JSR FAR. So that's all that I did with JFAR. Now, there's 2 missing commands in the kernel. There's stash and compare, where you're storing a value in another bank or comparing to a value in another bank. Since they're missing, I also included them in here. Now, each of these functions takes an extra byte. You have the accumulator points to a 0 page location, which holds a 16-bit value, which is an address. Your X register holds the bank number, and the Y value holds an offset from that address at that bank. It's exactly the same syntax that's used for the fetch subroutine in the kernel. The extra byte is a byte that follows the subroutine call. So JSR FAR is or SFAR is followed by, if you JSR SFAR, it's followed by a byte. And in much the same way that if you're calling JSR FAR, it's followed by a word and a byte. Similarly, CFAR, exactly the same thing. The accumulator is pointing to a zero-page location that has a 16-bit address, which is the address of the byte you're looking for, or at the starting address anyway. It's offset by Y. X is the bank number, and then the byte that follows is the byte you're comparing the address you're looking at with that byte that follows. SFAR, the byte that follows, is the byte that you're storing. So these two routines both use a small subroutine called GBYP. If you want to write a subroutine that similarly has, if you've got too many variables, you need just one more variable, and you want to have a subroutine call that is followed by a byte, then you can have the first instruction in your subroutine being GBYP, get byte. That byte will be extracted out of your code and placed in a location called BYTP. BYTP is actually this value here in the CFAR subroutine. If I hit F4, you can see BYTP is just that instruction right there, or that parameter right there. So then you can use that location of BYTP then within your subroutine, knowing that that's the extra byte that was added to the subroutine call, whatever subroutine call you made there. So those are a couple really useful subroutines that are down here in low RAM. If I go right to the very beginning, right at the very beginning of low RAM here, the first couple of commands are just, well, MP is the first one, then the second one loads the editor, and then the third one starts the editor. I'm going to go to mempee first. So what this one does, it sets 42 and 43 with 9F61. Now this did help. It did shorten some of the code. It saved me about 11 bytes in low RAM doing this, because then I could just use the store indirect to change the RAM bank. And the reason I did this, though, was because they are planning on changing the location of the ROM bank pointer and the RAM bank pointer to 0 and 1. And so when they do that, you can just do a poke, or two pokes rather. So you poke 0797 with 1, and then poke 0799 with 0, and it will change this for you. And so when they do that change on a future update of the emulator, you just need to poke those two values, and it will change the ROM bank pointer and RAM bank pointer in this low RAM. And then when it calls up the editor, once that update is done, the editor will also change, just the main program, not the metadata subroutines. And all it will change in them is the location of the ROM bank pointer and the RAM bank pointer. And when it sees that this change has been made, it will go through your program. It will go through the metadata that it has loaded up, and it will change any references to RAM-B or ROM-B to match what the values actually are in the new version of the emulator. This way you can write programs in this version of the emulator, and when they make changes that would otherwise be breaking changes, it will automatically be updated for you, and your program will still run. Down here you see hex D. It's just the hexadecimal characters 0 through F, And so that can be very useful to you. It's down in low RAM, just FD with an offset. And FNAM is a 32-byte buffer where I have file names. CBuff is a 32-byte buffer for, it's just a character buffer. I used it for everything you see on the screen right now. BASIC, BASC, it's at 0801. That's just the start of BASIC. So basically, that's a bunch of the useful subroutines I wanted to show you. There's a couple more. Let's go back up to the top here. When you're saving and loading subroutines in assembly language, you have to set the logical first and secondary address. Every time you want to load a program, it has to be 180, and every time you want to save a program, it has to be 181. So I've just included those as separate calls because you don't need to be setting A, X, and Y every time. Then you can just call this and it does it for you. Loading editor calls set name, and it's the starting point and the RAM bank pointer, and then it goes into here. Now, loading and saving directly into RAM banks is just doesn't work in the ROM right now because the file system uses RAM bank 0, and once it switches to RAM bank 0, that's the RAM bank number. And so in order to load and save files into RAM banks, you have to first load it into low RAM and then copy it up into banked RAM. And so what I've done is I have these subroutines here which copy, first of all, I've set aside bank FF for the purpose of building up strings, big strings, building up the list table, and also for copying whatever happens to be in 70038FFF up into bank FF. And then from there you can copy back down into there, or you can copy any bank into 7000 to 8FFF, or any from 7000 to 8FFF up into any bank. So all the loading and saving of bank RAM actually happens in low RAM, and it's all copied back and forth. And the reason I included this one here at the beginning here, this one here, this is so if your program is a big program and it goes all the way from 0801 even all the way up to 9EFF, say, it just takes all of low RAM. This just copies it, that section of your code, up into banked RAM while it messes around with all the loading and saving of banked RAM, and then copies it all back down with this call here. And these are the last two that I wanted to show you in low RAM. I think these are the last of the useful subroutines down here. Load bank and LB number X. If you have the file name stored in FNAM in 07C0 through 07DF, and the file name length is stored in FNLN, which just happens to be right there, then it will set that name, and then from bank X it will load the file. From bank X, it basically sets up, it loads the file into 7000, then copies it up, and then copies what was in 700 and had been pushed up into bank FF, copies it back down. And so basically, this is how I've been loading and saving all the banks. You can do the same thing if your file name is elsewhere. It has to be in low RAM somewhere. Your file name cannot be in banked RAM. It has to be in low RAM somewhere. But if it is already in there. You can just do the SNAM call yourself and then set X to the bank number and call LB number X. But if you copy the file name down into FNAM, then you can call LBNK with X set to the bank number, and it will do the same thing. So you can load banks yourself by calling these routines down here. And one final thing, if I go back to FNAM, FNAM and CBuff are both basically just character buffers, and they're each 32 bytes, and they're contiguous. And if you really need 64 bytes in low RAM, some subroutine that maybe you've got it stored in bank RAM, but you want it to run on a different bank or run on all banks, you can copy it down to FNAM temporarily. And the editor won't overwrite that area of RAM while your program is running, while you're exiting this program. But then afterwards, once you come back to the editor, all of that will be wiped out again. And I actually do this with exec. Let's see if I go meta and I load up the editor's metadata. Now I can go to exec and exe/ in a different bank. This actually copies this exe2 code, which actually does the exec of your function and then returns everything to the emulator. It actually copies this down to FNAM and does it there. So that's available to you as well. One little emergency chunk of 64 bytes in low RAM if you absolutely need it. So anyway, that's about it. This video is getting way long. Holy crap. I'll see you in another video.